Haven't reported anything in a while, but I thought this would be a good thing to do. We're going to talk about polar coordinates. And polar coordinates, I think you can boil them down to this question. So if you imagine a plane and you have the origin in the plane, polar coordinates, like any coordinate system, boils down to the question of how do I get from here to here? How do I get from the origin to a point in the plane? Now we're going to look at the different ways to do that, right? Uh, we already know one way to do that, and let me switch over here. Okay, so if you imagine a two-dimensional plane, and we're used to chopping that two-dimensional plane up into uh, from the origin, we have two axes, both of which pass through the origin. So we can chop that up into four quadrants, if you will. And then any point that we want to get to, say the point 1, 1 in Cartesian coordinates, we refer we're referring to how far along the x-axis and how far along the y-axis we move and in what direction. So the point 2, 2, for example, in Cartesian coordinates, we say we're going to move 2 units, right here, 2 units down the 2 units up the x-axis and 2 units up the y-axis, and that gets us to our point. Well, with polar coordinates, then we're going to navigate around the plane a different. So instead of moving uh, rectangularly, okay, instead of moving uh, horizontally, vertically, we're going to move along a circle. So what we'll do is we'll move a certain radius. Again, it's all with respect to the origin. So any coordinate system has to be defined with respect to something. So we'll have an origin. And instead of moving horizontally and vertically with respect to that origin, what I'm going to do is I'm going to move away from that origin, some radius, and then I'm going to move along a circle for some angle. Okay, so our coordinate system, instead of an XY and rectangular movement, we're going to still notionally have axes, but those are just references. We're talking about movement away from the origin, and then we're going to move some angle. And so, whereas before we had the X and Y axes as a reference, we'll leave those there, but now the references for the axes are angular references. Okay, so I'll move as you see from the shaded region, right? I move some R, in this case, that would be R equals 1, 2, 3, and 4. And then any point I want to get to, I get to by a rotation. So I can move an angle theta in the positive, that's counterclockwise direction, or negative, that would be the clockwise direction. Okay, so if I move R equals 4 and theta equals pi over 2, that's going to land me back on the axis here. Okay, pi is uh, directly behind the origin, right? 3 pi over 2 and 2 pi. Okay, so that leads to a couple things that I'll point out right here. One is that any point in the plane has multiple polar coordinates, right? That can get you there, multiple ways to get to the same point in the plane. And that was not the case in Cartesian coordinates. Okay. The way we think of movement, the way we defined it in Cartesian coordinates right? The point 2, 2, there's only one way to get there. Okay. With polar coordinates, okay, any point in the plane, I can get there. So here's, say, this point right here. Okay, I can navigate a certain distance, rotate up an angle. Now I can, if you remember, 2 pi is going to get you back to where you started. So if I go all the way around the circle again, I end up back at the same place. Or what if uh, instead of wanting to rotate in the positive direction, I rotate in the negative direction. Again, I can end up back at the same place. So keep in mind that polar coordinates will not be unique. So again, polar coordinates are circular movement. We still kind of notionally have the X and Y axes, right? So the pole is the origin, and all points in the plane then are defined being some distance r away from the origin and some angle theta of rotation off of the X or the polar axis. Okay, so again, if you look at this point, right, r theta, so r theta will get you any point in the plane, right? But that is not a unique thing, because theta could be this, or I could go all the way around the circle and back to the same point, or I could do it 2 times around a circle or 3 times, or instead of, as I move r away, instead of going positive theta, I go negative theta, end up the same place, or negative theta minus 2 pi, or and so on. You get the idea that there are an infinite number of ways to describe any point in the plane. So r theta plus 2 pi is the same point as r theta. Okay. We could also move a negative r, so that instead of forward in the what would be the positive x direction along the axis, we were to go backwards in the what would be the negative direction away from the origin, and then rotate our angle that way. So p r theta and p negative r theta are reflections through the origin. Okay, so they would fall along the same line, as you can see there. So now we want to do a little exercise, and we're going to start with 3 points in the plane, and we'll start with the point 1, 5 pi over 4, right? So we go a unit of 1 away from the origin, and then we rotate in a counterclockwise direction, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi over 4, and that is going to put us to there. What we want to do is, for that point, we want to think of, okay, how else could I get there? What are other ways to describe that same point? Well, what I could do is, instead of going, so go 1 unit away, I'm trying to get to the same point here, but instead of going 5 pi over 4, what if I go negative 1, 2, negative 3 pi over 4? Okay, so the point 1, negative 3 pi over 4 would get you to the same place. Okay, what if instead of moving 1 unit in the positive direction, I go negative 1 unit? So I go in the negative direction, and again, I rotate in the positive direction, but then I only need to rotate pi over 4, get to that same place. Okay, just an example of how I could get different points, describe different points in the plane with the same coordinate. Let's try it with negative 1, 7 pi over 4. Okay, negative 1, 7 pi over 4. Said I would go negative 1, and then 7 pi over 4. So that's 1, 1, 2, 3, 4, 5, 6, and 7 to get to here. Okay. Or maybe I do -1, but instead of rotating in the positive direction, I just go -pi/4. Okay, in the negative direction, get to the same place. Maybe I want to go in the positive, or maybe I want a positive r. So again, I go r=1, get to that same spot. I go 1, 2, 3 pi/4. Okay, so again, different ways to get to the same place. And again, on that reflection, okay, add 180 degrees gets you your reflection across the origin, right? So add pi radians to this 1 3 pi/4 point. That's going to give you 1 7 pi/4. That's not the same point, but it's the reflection about the origin. So it would fall on a straight line there. Okay, straight line through the origin. Finally, last example, we have the point 2, -3 pi/2. So we're going to go 2 units away from the origin. We're going to rotate -1 pi, 2 pi, 3 pi to get to the point S here. Okay, how else could we do that? Okay, well, we could have just gone 2 units and just gone pi/2 in the positive direction. It would have gotten us there also. We could go -2 units, -pi/2. Would have gotten us to the same place. Okay, just an example of how you have multiple ways of expressing the same point in the plane. Now let's talk about how do we convert between polar and Cartesian coordinates. So let's say you get an x, y coordinate, you want to move it to polar coordinates. So let's say you get a polar coordinate, you want to go backwards. How would you do that? And it all boils down to our friend, the right triangle. Okay. So if I look at this point in the plane, right, so if I describe that as moving x units in the horizontal direction, then moving y units in the y vertical direction, right, that describes a right triangle because the x and the y directions are perpendicular to each other. Okay, well, the radius of that same point, so the same point that has points x, y, and r theta, where I go r units away, rotate up theta to get to that spot. Okay, so the point P can be described as r theta or xy, depending on the coordinate system. Well, looking at that triangle, right, I've moved r away, I've rotated up theta. Well, that theta is one of the angles of our right triangle. Okay, now the obvious thing that jumps out, it's a right triangle. So the hypotenuse of our right triangle is r, and r² = x² + y². Okay, so if I have the x and y and I want to know what r is, easy peasy, r² = x² + y². Okay, going back to our friend, the right triangle, right? What do I know about the tangent of the angle theta? It is the opposite over the adjacent. That would be y/x. Okay. The cosine of the angle theta, cosine would be the adjacent over, that would be x over the hypotenuse r, which means that if I solve for x, x = r cosine theta. The y here, okay, if I want to know the sine of y, be the opposite over the hypotenuse, that would be y/r. Solving for y, we get y = r sine theta. And those are your formulas that you use for converting from polar to Cartesian coordinates and back. So a point with polar coordinates r theta, Cartesian coordinates x, y. Okay, if that is the same point, then x will equal r cosine theta, y will equal r sine theta. Okay, and a Cartesian coordinate point xy, polar coordinates r theta. Those are the same point if r² = x² + y², and the tangent of theta is y/x². x. So let's look at an example. We'll look at the 0.2 3 pi over 4 here. Okay, we don't even really need to graph it. We can kind of see where the thing is. And so that tells us, if we kind of put that point in, that that is going to be in the second coordinate. So we expect a positive y and a negative x, just as kind of a reality check. So let's do this. So this is our theta, and so our xy, so the xy point, that's going to be r cosine theta. So that would be 2 cosine 3 pi over 4. And the y coordinate is going to be 2 sine 3 pi over 4. Sorry about running out of room there. Okay, cosine of 3 pi over 4 is root 2 over 2. So this is going to be 2 times the square root of 2 over, negative square root of 2 over 2. And the y coordinate will be 2 times the positive square root of 2 over 2. So those cancel, right? I get negative root 2 comma positive root 2 as my x and y coordinates. All right, now let's do another. So let's look at the case where we are going to convert from rectangular to polar coordinates. So let's suppose that the point is 1, 1. We'll locate it down here. So we see it's 1, 1. All right, so our tangent of theta is y over x. We have r squared equals x squared plus y squared, and our xy is 1 minus 1. Okay, so it helps when you're converting from Cartesian to Cartesian coordinates to polar coordinates. It helps if you plot the point, because we want to make sure that we get the correct angle theta. Okay, so we'll typically end up having to use an inverse tangent, right? So the inverse tangent of y over x is going to be our angle theta, and we want to make sure that we're picking the correct angle theta. Remember, the inverse tangent is going to give you an angle between negative pi over 2 and positive pi over 2. Right? That's the only place it's defined for. And so if we have anything outside of that, then so that means that's going to give you an angle, but that's down between negative 90 degrees and positive 90 degrees. So that's only going to cover this half of the circle, the right half of the plane. So if you're in the other half of the plane, then you need to know, okay, I need to get an angle that's in the other half of the plane. So when you get that output from the inverse tangent, you'll need to adjust it appropriately. Okay, so we'll do this first, and then maybe we'll look at an example where that's not going to be the case. Okay, so let me sorry, this is actually, I should say 1 minus 1 and negative 1 in a second. Okay, just to do that. But let's switch over. Okay, switch over to the whiteboard. Okay, so we're going to do this one first, and then I'll do the negative 1. So let me get it out of here so it's not confusing first. So let's start with r. We have r squared equals x squared. That's going to be 1. Y squared minus 1 squared is 1. And so that's 2. And so that tells us r equals the positive square root of 2. Okay, the tangent of our angle theta is going to be y over x, so that's negative 1 over 1, or negative 1. So if I do the inverse tangent of minus 1, okay, there's a couple of ways I could do that, right? I could do the inverse tangent of minus 1, see what I get out, or I could just think, right? So that means if it's the inverse tangent, so I need tangent as minus 1, which means my sine and my cosine have to be the same. And that's going to happen along the pi over 4 markers, right? Pi over 4, 2, or negative pi over 4 in this case, right? So I need them to be the same magnitude, but opposite signs. So that'll happen for negative pi over 4. Either way, if I do the inverse tangent, it's going to give me negative pi over 4. Okay. And so the r theta that we want in this case is going to be square root of 2 negative pi over 4. So square root of 2 negative pi over 4. It's going to give me that same place. All right. Everything checks out. All right. Now let's switch this. Okay. Now it's negative 1, 1. Okay. So we're going to switch this because it's going to be slightly different for us. Okay. So let's. Okay. R is going to be the same. Okay, now it's going to be minus 1 squared. That's 1. 1 squared is 1. That's 2. R is still going to be the square root of 2. But now, the invert, we get tangent of theta is going to be y over x again. And that's still going to be minus 1 in this case. Okay, but now, if I blindly stick this into a calculator, it will give me negative pi over 4. Okay, well, negative pi, that's down here. That's not where I need to be. I know I need to be up here. Okay, so what do I do to fix that? Well, remember that tangent has a period of pi. So if I were to, so what we need is we need the tangent of theta to equal minus 1. Okay, so tangent of minus pi over 4 equals minus 1, sure, but that's not the angle we need. We need, so if we just add pi to it, that's going to give me pi. That's going to put me back in the quadrant I need to be. And so that's going to be the correct answer. And so theta, instead of being just the output of the inverse tangent function, because remember, inverse tangent only is defined from negative pi over 2 to positive pi over 2. When you're outside that range, you need to adjust, you need to think. Okay, so your inverse tangent might give you something over here. You're going to have to adjust to get to here, or in this case, it tells us the points down here, but we know the points in the second quadrant, not the fourth. So if we add pi to it, that will get me the correct value, which is going to be 7 pi over 4. And so the r theta that we need in this case is square root of 2 7 pi over 4 for, that's the point, minus 1. All right, so that's just a word of warning, something to pay attention to. It helps to plot the point so you're solving for the right thing. You know that the output makes sense. All right, now we can talk about graphing some basic curves in polar coordinates. Okay. So we'll start with a circle of radius, absolute value of A. Okay, well, just the nature of polar coordinates, simply R equals A. All points A away, whether A goes in the negative or goes in the positive direction, R equals A is going to give you a circle of radius, absolute value of A. Okay, a line through the origin, simply defining an angle theta for any, so it's any R, but theta equals theta naught in this case. That'll give you a line through the origin. Okay, you can get some more clever curves like R equals theta. Okay, so as theta increases, R increases. You can see that's going to be a spiral that winds outward from the origin. Okay, we can also describe some more complicated circles. So to see how to graph something like that, let's actually approach it from a different way. Let's look at what would this equation. Okay, so if I wanted to graph this equation, how would I do that? All right, so what we're going to do is we're going to convert this to Cartesian coordinates. So one common thing is to try and convert this to Cartesian coordinates. Okay, so remember that, oh, this is actually, so I put the wrong thing. All right, so we have R equals 10, should be this, 10 cosine theta plus 24 sine theta. We're going to multiply both sides by R to get 10R cos theta plus 24R sine theta. Okay. Well, one of the reasons that we can do that is remember that X is R cos theta, Y is R sine theta, and R squared equals X squared plus Y squared. So the left-hand side is X squared plus Y squared. R cos theta is X. R sine theta is Y. And so this is 10X plus 24Y. Okay. Now, at this point, okay, we got an X squared plus Y squared. Maybe that kind of looks like a circle. And so what we can do is we can get all the, oh, this is Y. Get all the X's and the Y's on one side. Okay, and now we're going to do the old complete the square. Okay, so if we complete the square, then what we have to do is we got to say, all right, so we want to turn this into a perfect square. And so a perfect square, X minus A squared, say, is going to be X squared minus 2A times X plus A squared. And so what we want to do is we want to figure out what that A squared is we need to add. But we notice that minus 2A is going to be minus 10, right? Those coefficients would have to be the same. So A is 5. And so if I add 5 squared, that's 25, Okay, well, I got to do that over here too. So I'm going to add 25 over here. Same thing here, but now that negative 2a is minus 24. And so the a would be 12. And so if I add 12 squared, right, to both sides. Okay, so that's completing the square. Just to erase the scratch work real quick, but that should hopefully be mostly a review. It's um, I understand it's like something you do a little bit and you kind of forget because you don't do it, then you're supposed to know it. So just refresh your memory on completing the square. It's critical tool to have in your toolbox. So just kind of remember that. All right, so that means that if we add a squared, that this is x minus a quantity squared. So we added 5 squared. So that means this whole thing collapses into x minus 5 quantity squared. We added a 12 squared. So this whole thing collapses into y minus 12 quantity squared. And so then 144 plus 25. Okay, 144 plus 25 is 169, and we can check. That's 13 squared. All right, so now this is a standard form of a circle. Okay, that standard form of a circle of center, right? It's the standard form of the circle is x minus h squared plus y minus k squared equals r squared. That's a circle with center 5, 12, and radius, if it's r squared, so radius 13. All right, so if I wanted to describe this circle, I could do so with r equals 10 cos theta plus 24 sine theta to see what that was. We just did a little bit of algebra, and we can see that that gives us circle of radius 13 with center 5, 12. Okay, so circles in polar coordinates, just kind of generalize that. The equation r equals a is a circle of radius, absolute value of a centered at the origin, 0, 0. If we want to center it elsewhere, the equation r equals 2a cos theta plus 2b sine theta is a circle of radius a square root of a squared plus b squared centered at a, b. Okay, so to go back to our original thing, okay, we had 10 cosine theta plus 24 sine theta. So 2a was 10, that means a was 5. 2b was 24, so b was 12. And sure enough, that does match what we got when we did the completing the square. So I want to wrap up then with a quick discussion about symmetry for polar equations. So symmetry about the x-axis occurs if the point r theta is on a graph whenever r minus theta is on a graph. And so let's look at a symmetry about the x-axis. Okay, r theta is on the graph, r minus theta is also on the graph. And then the graph would be symmetrical about the x-axis. We're symmetrical about the y-axis if the point r theta is on the graph whenever negative r negative theta is on the graph, or another way to look at that is r pi minus theta. Okay, so r theta is on the graph, negative r negative theta also on the graph. And again, we can always express points multiple ways, so that would mean r pi minus theta also on the graph. However you want to look at it, that's symmetry about the y-axis. Finally, symmetry about the origin. R theta is on the graph, negative r theta is also on the graph. Okay, so r theta on the graph, negative r theta also on the graph. And again, we could describe that point the same way as r theta plus pi. Okay, that would get us that same point, negative r theta. All right, so those are the three basic types of symmetry that we'll look for with polar coordinates. And for an introduction to polar coordinates, I think that will do it. So